So we've turned a corner now. We learned our first real hypothesis test for numerical variables, right? That was the t-test. We can compare the means of two samples, representative of two different populations, and we could determine with a certain level of probability that the means of the two populations were different. Okay, that was our objective, to show that the means of these two populations are different. That's usually what we're after, isn't it? I mean, because usually we're doing studies to show that an intervention that we're planning is going to be effective, that a drug works, that one group, a certain diet may be more protective than another diet, and so on. So we're usually in a situation where we want to show that there's a difference between two things. Problem is when we measure something, especially something numerical, if we measure something, we measure weights or BMIs or vitamin D levels in blood and so on and so forth. If we take measurements like that, if we took them from the same population, the same group, and took two samples from that same population, the means are going to be different, right? Just by chance, one group is going to be almost always going to be bigger than the other group. In a rare situation, we're going to find two means that are exactly the same when we take a sample from a single population. It's kind of like flipping a coin and having it land on its edge. You know, it's going to happen every once in a while, but not very often. So the real key is that now when we're really testing two different populations and we want to see if the means for those populations are different, we now have to figure out whether the difference that we see in the sample means that we get from each one of them, if that's due to chance, the way it is by taking a sample from the same population, or if that's due to an actual difference in the mean of the two populations. And that's why we did the t-test. T-test was a way for us to, with an understanding of how sampling works and sample means work, a way of predicting how likely it would be that we would be wrong if we said those two means are different. In other words, how likely is it that we'd be wrong if we said the difference was not due to chance, but to an actual difference in the two populations? That's great. Great tool, works terrific. It's got two basic, our immediate problem with that is it's got two basic drawbacks. One is that it only works for two means, right? We didn't talk about, well, what if you got three? What if you got three populations? You have population A, population B, population C. How do you deal with that? How about if you have 8 ethnic groups and you want to evaluate a numerical variable to see if there's a difference between each of the 8 ethnic groups? Well, now what are you going to do? You're going to do a mean of 1 and a mean of 2 and a mean of 3 and you're going to compare 1 and 2 and 2 and 3 and 2 and 4 and 1 and 5. You get to the point where you're going to wind up doing a lot of t-tests. And remember, what was our level of error that we would tolerate in the t-test? Remember what it was most of the time? Most of the time, we're looking for an alpha of 5%. So if we wind up doing a t-test 20 times because there's 8 different groups, right, or whatever it is, 8 factorial, whatever that comes out to, 7 factorial, whatever that comes out to, right, that number of possible combinations, eventually we're almost sure to get it wrong, right? It's kind of like playing Russian roulette over and over and over again, right? So that's not going to work so good with multiple groups. Works great with 2 groups, doesn't work so good with multiple groups. Next week, we're going to learn about something that's going to help us with that. It's called analysis of variance. It's basically a way to do what we did with the t-test, but with a situation where we have multiple groups. So that's one issue we got with the t-test and the hypothesis testing we've been doing so far. Works great for 2 groups, doesn't work so well for multiple groups, comparing multiple groups at the same time. The other problem that we have is it's for numerical variables. Not all variables are numerical variables. I'll give you an example. Let's say, let me get this out of the way. Okay, let's say they have a situation where, I'm trying to think of something that's in the news recently. I'm going to talk about Legionnaire's disease. Okay, let's say I have a population of 200 people, right? And 200 elderly people in a nursing home where they've had an exposure, where they would have an exposure to Legionnaire's disease. Okay, and they suspect it has something to do with a particular a particular hydrotherapy bath in the building. And they say to themselves, "Oh, 200 people were involved here. 100 people used that bath, and 100 of those people did not use the bath." Okay, so now 100 used the bath, 100 didn't use the bath. Well, we noticed that we had 30 cases. I'm going to make it a little bit bigger. Say 40 cases of Legionnaire's disease. Oh my goodness! Oh, what happened there? Okay. Oh, okay. Oh, I'm sorry. That only affected you. I think the guys online could see it. It was waiting for me to run the plugin again. Usually after the first time, they must have been playing around with this. Usually after the first time you run the plugin, you really don't need to do it again. Okay. Okay, let me move this over. Okay, I had a lot of things to get out of the way here. How's that? That better?
That's great.
Okay, good. All right. Okay. So, how are you guys online doing? Can you hear me well, and can you see the board? I believe you can. Okay, good. All right, so 40 people wound up getting Legionnaire's disease. Okay, so it didn't seem so clear. Maybe not everybody that used the bath clearly got Legionnaire's disease, and maybe there were a few other cases that, like, they're not sure how they got them. So let's say 40 people got Legionnaire's disease out of 200 people in the population. What's the prevalence of Legionnaire's disease? In this case, probably the incidence, but let's call it prevalence for our purposes. What's 40 out of 200, right? So 20% of the population of this nursing home had symptoms of Legionnaire's disease, okay? Or maybe some other pneumonia, whatever it happens to be. So let's say now you want to take a closer look at this. So you could take each person and you could say, okay, patient one, okay, did he have did he use the bath? Let's say he did. Did he get Legionnaire's disease? Oh, let's say he did. Patients two, did they use the bath? No. Did they get Legionnaire's disease? No. How about patient three? Yes, they used the bath. No, they didn't get Legionnaire's disease. How about patient four? No, they didn't use the bath, but they got Legionnaire's disease. How many variables do I have here? I have two, right? How do you figure I have two? I have one, which is the exposure, use the bath or not, right? And the other one is the outcome. They had the disease or they didn't get the disease, right? So we have two variables. One variable, the variable number one is exposure, right? And the variable number two is disease, yes or no, okay? Or I'll call it just LD. Well, I'm going to summarize the data for these two groups. And the way I'm going to summarize it is I'm going to create a table. Remember those tables that we used for diagnostic tests? It's going to be very similar. We call this a contingency table, right? Sometimes they call it crosstabs. And in the rows, just like before in the rows where it's a test, I'm going to put, instead of test, I'm going to a diagnostic test, I'm going to put the exposure. So yes, they used the bath. No, they didn't use the bath. Okay, in the columns, I'm going to put the outcome. Yes, they got Legionnaire's disease. No, they didn't get Legionnaire's disease. Okay, so how many people, what did we say? 100 people used the bath. So there's 100 in the columns, right? Yeah, in this row, yes. And 100 in this row, no, didn't use the bath. Well, out of the 100, you can't tell from what I've told you before how many people use the bath. How many people use the bath wound up with Legionnaire's disease, how many that didn't use the bath wound up with Legionnaire's disease, right? Because I haven't told you that. I've only given you the basic outline. There were 40 cases and 100 people used the bath. You don't know how they would distribute it yet. Now I'm going to ask you, if there's no association whatsoever between using the bath and Legionnaire's disease, what would you expect to have the number of people that used the bath and got Legionnaire's disease? Well, out of 100 people that used the bath, how many people would we have expected to get Legionnaire's disease? Remember what the prevalence was?
20.
Yeah, we'd expect 20 out of 100, right? You guys all agree with that, right? And that would leave 80 that didn't get Legionnaire's disease. How about the people that didn't use the bath, the 100 people that didn't use the bath? Prevalence is still 20%, right? So if there's no association, bath had nothing to do with it, we'd expect 20% of them to get it too. So this would be 20 and this would be 80. That's what we call our expected values. That's the way that we would expect this distribution to be occur in these tables if there's no association between the exposure and the disease. Now, let's take a look at what we actually observed. Okay, I'm going to make another table, same table, except this time, oops. Get close to the edge, I guess. Okay, except this time, I'm actually going to count the number of people who got the disease, survey them, did they use the bath? Turns out that 30 people that used the bath got Legionnaire's disease, 70 did not. 10 people now we know it has to be 10 because there's 40 cases altogether, and 90 people did not. And this is for the exposure, yes and no. So, remember I told you before that we get into a lot of situations where we expect in a perfect world, if we had 40 cases among these 200 people, we'd get at least 20 people in here and at least 20 people in there, right? But in the real world, even if there was no association, I might find that there might be 18 in here and 22 in here, or 15 here and 25 here, just by chance, right? You guys agree with that? That could occur by chance, that it wouldn't wind up with the perfect situation that we would expect 20 and 20. In fact, it would be unusual for that to happen perfectly, right? There's a lot of odd things that would have to happen, a lot of chance that would have to get eliminated to have that occur. Okay, so now the real question now is, we see that there's a difference between our observed values and our expected values. Now our task is to say whether or not the difference is big enough to say with less than 5% chance of being wrong, is the difference big enough between the observed values and the expected values, big enough for us to say that they're really different, that there is an association between using the hydrotherapy bath and the outcome having the disease, right? So we have to determine whether or not, same thing we did before, except then we did it for numerical variables. Now we're doing it for a categorical variable. It happens in this case that the categorical variables, the two categorical variables, in this case, have two values, like use the bath, didn't use the bath, got the disease, didn't get the disease. You could also imagine this could be for, like multiple values. For instance, it could be the exposure, and then it could be Hispanic patients, black patients, white patients. So we can have a number of columns, number of rows, and so on and so forth. We're going to stick to two by two tables for now, just for simplicity's sake. But this works with any categorical variable, even if there's more than two possible values that it could have. But right now we're dealing with just two variables and two possible outcomes for each one. Okay, so now how am I going to determine whether or not this is a likely outcome to occur? Okay, I'm going to carry this over here. Okay, and hopefully I won't mess this up too much. 100, 100, and well, let's see. Yes, no, the exposure, and this is yes or no for disease, and this was 30 and 10. These are our observed values. 70 and 90. Okay, and down here are our expected values. These are our observed, and that's our exposure. And down here, going to be 20, 20, 80, and 80. Okay. Now notice that had this been 50 people that weren't exposed, then this number would have been 10. Would have been the same ratio based on the prevalence. Okay, so it just happened I gave you a nicely evenly divided population. It's not always going to be that way. Could have been 50 in there, in which case the expected outcome would be 10 out of 50, 20%, and 40 not getting it. Okay, and this is our expected values. Okay, so what I want to see is I want to see each one of these boxes, this box for observed value and this box for expected values. The bigger the difference is, the more likely that it's not due to chance. That makes sense? You guys okay with that? In other words, if the difference between this and this is small, there's a good chance it could be, there's a better chance it could be due just to chance than if those differences were big, right? If there was no association between the hydrotherapy bath and Legionnaire's disease, I wouldn't expect to see a big difference in the two groups. I'd expect to see a difference, but not a big one. So the bigger the difference is, the more, like for instance, if I took the extreme and I said 40 people that used the hydrotherapy bath got Legionnaire's disease and none that didn't use it, you say, well, it's pretty clear that it's due to the hydrotherapy bath, right? Okay. A lot of times we're going to wind up more with a situation like this where there's a difference, but now you have to make a judgment as whether it's a big enough difference. So I need to quantify how big the difference is. Okay, and the way I'm going to quantify how big the difference is I'm going to take the observed values, I'm going to subtract the expected values from it. That will give me the difference, right? So I'm going to take the observed values, the observed values minus the expected values, right? And so that's going to be 10. Okay, this one is going to be minus 10. This one's going to be plus 10. This one's going to be minus 10. So when I add the differences together, I wind up with the same problem I had before, right? All of the differences add up to 0. How did I get around that when I was doing sum of squares? How did I get rid of the positive and negative numbers? Make them all positive. Square them. Let's square this. Okay, let's square it this time instead. And you want to know something? What else did I do in order to get back down to within the range of the actual values and numbers? I divided by the sample size, right? Well, in this case, I'm going to say, let's square these and then divide by the estimated value to get it back into the range of numbers that would have been. This will give us all positive values, and this will get us back into the range of what the differences really were. Okay, so what I'm going to do now is I'm going to add up observed minus expected, square it, and divide it by the expected. Okay, and I'm going to do that for each box. And the way that might look if I was writing a formula for that is it might look like the sum of the observed minus the expected squared over the expected, right? For all 4 boxes, right? Equals 1 through 4, all 4 boxes. Okay, so I'm going to go ahead and do that. So 30 minus 20 is 10, squared is 100. 10 minus 20 is minus 10, squared is plus 100. 70, 80, 10 squared is 100. 90, 80, 10 squared is 100. So I wind up with, okay, so hang on a second. What I didn't do though is this first one, 30 minus 10 is 100, but I got to divide it by 20. And this one, 10, okay, that's divided by 20. And this one, 70, that's 100 divided by the expected value divided by 80. And this one, 90, 80 divided by 80 again. Okay, so what do these numbers come out to? 100 divided by 20 is 5. 100 divided by 20 is 5. 100 divided by 80 is 1.25. 100 divided by 8 is 1.25. So if I add up, if I take the sum of all of these differences, okay, it adds up to 10.5. Okay, so I'm going to give that value a name. It's a statistical function. I'm going to call it chi, that's a capital chi, squared. That's the sum of each one of these. What I did was each box I took the observed minus the expected, which is 10. Yeah, it's the sum of these numbers. Isn't it? I'm sorry, 12. Excuse me. You're right, 12.5. I'll show you again. I take 30, the observed, minus the expected is 20. Square it, that's 100, and divide by the expected value, 20. And that's where that 5 came from. Yep. See, this is divided by 20, 20. This is 80 and 80 because there were these two boxes, these two expected values.
I just have a quick question.
Sure.
Like what you did, like the bottom math, like what's above that? Like when you do like minus 10, whatever.
Yes.
Is that important to the steps, or you're just showing?
No, I was just showing you. I was just showing you that, like the logic behind, squaring it and then dividing by expected value. Okay, there's better logic for it, but I think that's a decent, simple explanation for it. Okay, so this value now is our chi-square value. Okay, so chi-square is a new statistical function for us, like t was a statistical function. Okay, except now we have, just like we had a normal distribution for z, we had a t distribution for all of its different values of sample size. Now we have a chi-square distribution. And again, there's a different chi-square distribution for different degrees of freedom, just like there was for the t function, t distribution. Okay, except there's a little bit different way of how we figure out what the degrees of freedom are. So I'm going to draw quickly. What do you think this might look like? Okay, if we were going to take a situation where there's no association between the exposure and the outcome, right? Would you expect the difference between the two of them to be 0? I mean, that could happen, right? But is it likely to be exactly 0? That the two observed and expected values are exactly the same? No, probably be a little bit off. So actually, the probability of them being 0 difference for probability of chi-square after you do this whole function being 0 is actually not all that great. It might be down here somewhere. And then it goes up for a while, as you get to an area that you would expect that kind of, expect that kind of a little bit of difference. And then as the number gets bigger, chi-square gets bigger, it's less and less likely that you would get that big a difference between the observed and the expected values. Okay, so as chi-square gets bigger, right, this is the probability, right, and as chi-square gets bigger, it's less and less likely that you would get that outcome from if there was no association. Okay, so this is 100% of all the outcomes that you would get if there's no association. So in order for us to say that there's a difference, we would have to go way out here, way, way, way out here. The only problem is we really need a big sample size. And this is almost kind of asymptotic. You may never really quite get to 0 probability, right? Until you actually had, like 0 in one group and infinite in the other group or something like that, right? So because we're willing to accept 5% chance of being wrong if we say that they're different, we cut off the chi-square value that we want. We cut that off where this area in here is equal to 5%. What does that area represent? That area represents that 5% of the time that you could get a chi-square that big if there was no association between the two groups, between the exposure and the outcome. So a chi-square, anything bigger than that would only happen less than 5% of the time. So that's where our error is. 5% of the time, we might actually get a chi-square value that's this big or bigger, if even though there's no association between the two groups, between the two variables. Okay, but we're willing to take that risk because we live in the real world. I mean, we have to at some point say that we're sure enough that we can call this a significant finding. Okay, so what's that value going to be? There's a table that we can go to look that table up. Chi-square table. Okay, it's on Blackboard. Let me see if I can't find it without going too nuts. Square table. Here we go. Let's take a look what that table looks like. Oops, there's a cooling, there's a evaporative condenser or a dry cooler or something. Okay, here we go. This is our chi-square table. These are the number of degrees of freedom. These are the probability of exceeding the critical value if there's no association. In other words, making a mistake if we reject the null hypothesis. Now I'm going to tell you how to calculate the degrees of freedom. The degrees of freedom are equal to the number of rows minus 1 times the number of columns minus 1. So what do you think the degrees of freedom for our purposes are? Degrees of freedom, number of rows minus 1 is what? 1. Number of columns minus 1 is 1. 1 times 1 is 1. We're working with a distribution that's 1 degree of freedom. If we had 2 rows and 4 columns, that would be 2 minus 1 is 1 times 4 minus 1 is 3. 1 times 3 would be 3 degrees of freedom. Okay, if we're 8 rows and 8 columns, it would be 7 times 7 or 49 degrees of freedom, right? You're not going to run into that very often or at all. Okay, so what value does chi-square have to exceed in order for us to say with 95% certainty, in other words, with less than 5% chance of being wrong, our acceptable alpha, what value does chi-square have to exceed in order for that outcome to come up less than 5% of the time? You guys see it there? What is that? It's 3.841. You remember what we calculated?
12.5.
Yeah, 12.5. So what do you think? Do we reject the null hypothesis? Right? Our chi-square we calculated is bigger than our critical value, right? Which means that it's further out on this distribution. It's way out here. So it would happen, well, hang on. So it would happen less than 5% of the time if there was no association. So our null hypothesis is that there is no association, but this value that we got for chi-square is so big, the differences are so big, that we can reject that idea and say that there is an association. Remember, now's a good time, I think, it's a little late, but now's definitely a good time to look at what is our hypothesis here. What's our null hypothesis here?
Right. There's no association.
No association between the bath and LD. And what's our alternative hypothesis? There is an association, right? And in order for us to prove that there's an association, there has to be a big difference between the observed values and the expected values. And the difference turned out to be 12.5. But anything over 3.8 would have been big enough for us to say that there is an association. Look how big the difference is, right? So if it had been a 3x2 table, which would have been 2 degrees of freedom, then it would have had to have been 5.91. If we wanted to be 99% certain, and for our 2x2 table, it would have had to have been 6.6. Those are the critical values for T, for the chi-square rather. Okay, you guys okay with that? It's really pretty simple, right? I mean, it's not like a complicated, convoluted theory buried in theory and integrals and so on and so forth. It's really a pretty simple concept. We're looking at the differences between what we observed and what we would have expected to observe. Yes?
Okay, so if we were to get this question on a test, and
Yes.
just say, like, this is the prevalence.
Yeah.
And then we took a sample of this many people, and this is the observed value.
Right. We took a sample. We'd have to tell you that there are so many people were exposed, and of those number of people that were exposed, that 12 of them got the disease. And this is the number of people that weren't exposed. And of the ones that weren't exposed, 9 people got the disease. Because without knowing that, you wouldn't be able to fill in your observed values. But once you got your observed values, let's go back and take a look at that. See, if I had given you the other table first, your observed values, you could have said to yourself, could you have figured out the prevalence from your observed values? right? How would you have figured out the prevalence? You know, 40 people had the disease. So out of the total sample, out of 140 people, out of 100 people, 200 people that we sampled, right? So 40 out of 100 is 20%. So you could then go back here and say to yourself, well, for 100 people, I would expect 20. If there were 100 people that were exposed, I expect 20 of them to get sick. 100 people weren't exposed. See, now on the other hand, if it had been 60 people and 140 people, then it would have been 20% of this would be 12, and 20% of this would be 28, and then you'd fill in the rest. Okay, so you could actually do, from a description like that, you could actually fill in the observed values and the expected values. Okay, and in fact, if I go back with just a little bit, very often we might just give you a table with the observed and the expected values and ask you to go ahead and work with it. Okay, or we might just give you the observed values and ask you to create your expected values. There is a chi-square function in Excel, matter of fact. You know, I hate doing stuff like this. Usually when I'm doing a demo in class, I like to have done it in the last 10 years. But because of SPSS, I rarely do this anymore. There is a chi-square calculation in SPSS. The only downside of it is there's the version without special plugins that comes built into Excel doesn't give you the expected values. You have to find that on your own. So in other words, if I were going to recreate what we just did, 30 and 70 and 10 and 90, okay, for our table, there's a function here equals chi-square, okay, parentheses, chi-square dot distribution, parentheses. No, that's not what I want. Chi-square test, I think I want. There you go. See what it's asking for me there? See what it's asking for there? It's kind of really tiny, unfortunately. But what it's asking for now, chi-square dot test, is asking for the actual range and the expected range. We have the actual range. Here's the actual range here, observed values, comma, and now we got to give it the same box which represents the actual range. I'm going to do it. Hang on a second. I know it's 20 and 80, right? We calculated that already. And 80. Okay, so I'm going to give that a try. Equals chi-square dot test, parentheses, and the actual range is this. These are the observed values, comma, and the expected values, expected range or values is that, those four boxes. And it comes out to that. Okay, that's the probability. The probability is less than what critical value that we want for probability? Less than 5%, right? Okay, if I actually want to know what the chi-square value is, equals chi inverse, I think it is. See, like I said, I hate doing this if I haven't done it for a while. The probability, comma, degrees of freedom, 1, okay, 12.5. Same thing we calculated. The test I just showed you, right, gives me the p-value, the actual probability of being wrong if you reject the null hypothesis. Before, we didn't know what that was. All we knew was that we had to exceed 3.8. And if we exceeded 3.8, the probability would be less than 5% that we're wrong. Well, in fact, you could tell 3.8 versus 12.5, the probability is going to be really small that we're going to be wrong. And in fact, it came out to like 0.04 of 1%, right? 0.0004. In Excel, and the function that I did, the chi-test, actually gives you the p-value, not the chi-square value. If I want to know what the actual calculation for chi-square is, it's going to be equal to chi inverse, right? That's the function I would use. And it asks for what's the probability, which is what we just calculated, comma, number of degrees of freedom, which is 1. And it came up with the number we calculated from before. Now, we did this manually. We could have used Excel to do all these calculations. And in fact, we could use SPSS to do these calculations as well. Let me open up Blackboard. I believe I have a data file that we can use. let me tell you, it's so much nicer to have people reacting to this, so I know if it's coming across. Okay, let's see. Okay, let's see. Materials. By the way, would you guys like to have the test next week or after Thanksgiving?
Next week.
Next week, so you can do it over Thanksgiving weekend. Yeah, and a couple other people were. I'm going to put up a quick survey. So it would be a nice point time to break. So we just do the t-test and
We
chi-square.
have a lot of stuff after Thanksgiving.
Yeah, okay.
too.
I think you're. I'm gonna put up a quick survey tonight, just to get some feedback from the rest of the class. Yeah, you guys you guys are the tip of the iceberg, right? Yeah. Like there's 60 people in this class, or 55 or something like that. So we don't see the rest of them, unfortunately, but there are quite a few of them. As a matter of fact, they're listening to me online. Some of them. Hi guys. Okay. Okay. So let me go here. Let me get to one of these. I didn't put the lecture up, did I? Ugh. All right. It's been a bad week. Okay, I'm gonna see if I can. I'm gonna download this. Okay, I think it's on the desktop. Okay, gonna open up. There's. I have a file on there. Stenosis and smoking. You guys know what stenosis is, right? It's like narrowing of the coronary arteries. It's called stenosis, right? They call it when they open it up. They call it a stent. I guess it comes from Greek or something. Okay. Hopefully the date is there. Get this out of the way. Here we go. Okay, so here we have some data here. Each one of these rows represents a patient, an individual, a person, right? And we have three columns. We have three variables. One of them is whether the person's a smoker or not. The next one is whether they have evidence of stenosis, narrowing of the arteries. And the third one happens to be gender. If I go to the variable view, if I'm lucky, in fact, if I go into smoking, it tells me a 1 means yes and 2 means no for smokers. Okay, and how about stenosis? Okay, let's see, presence of stenosis. 1 means yes, they have it, they have the disease. 2 means no, they don't have the disease. So I need to organize this data. Now notice SPSS likes the data the way that you would collect it. As you test patients, you put in the result. Is he a male, female? Does he smoke? Does he have stenosis? You would put this in. All of these are categorical variables, nominal or categorical variables, right? As in the last case we had, each one of them only has two values, a yes or a no. So now I need to organize this into a table. How many people have this disease? How many people are smokers, and so on and so forth? And I probably want what I did before. The exposure in the rows, the exposure would be smoking, and the outcome or the disease in the columns, which would be stenosis. Okay, so I'm going to try and organize it that way. I'm going to go to Analyze, and I'm going to down here. I hate this. Okay, let's see. Can I better? So, t-tags. I'm going to go into descriptive statistics. As it happens, SPSS organizes this into descriptive statistics. I think because because organizing this crosstabs or this contingency table is kind of a way of describing the population, even though we're doing a test with it. Right? It's kind of a descriptive operation. So I'm going to go into crosstabs, and in crosstabs, I can tell it, what do I want to put into the rows? Well, I'm going to put the exposure into the rows, smoking. What do I want to put into the columns? I'm going to put the outcome into the columns. Now, I could have put gender as an exposure instead, right? But I just chose to use smoking first. Okay, so now I have a bunch of options I have here. Statistics. Right now, it's not going to do any statistics at all. I can see chi-square up in the corner there. That's of some interest to us, right? Let's go into cells. Right now, it's going to give me it's going to organize this into the observed values. That's all it's going to do, just observe values. If I want expected values, I got to click that. I'm just going to do that right now. I'm going to let SPSS organize this for me.
You already know.
I'm in, I'll go back and do it again. Hang on a second. Okay, analyze,
I have that.
descriptive statistics. I'm going to go into crosstabs. Click on crosstabs. A window comes up. It's got rows and columns. I'm going to put smoking status into the rows. I'm going to put presence of aortic stenosis into the columns. Okay, good. So now I'm going to go into the cells, and I'm going to make sure it's just going to give me the observed values. Okay, and I'm going to click OK. Okay, and it actually organizes this for me. I'm going to squeeze this up a little bit so I can get it up high where you guys can see it. So what is it? Well, let's see, how many people were in this study? 215 people in this study. How many of them smoked? 94. How many of them didn't smoke? 121. How many of them had, had stenosis? 98. How many of them didn't? 117. If I asked you the prevalence of stenosis in this population, what would you say it is? 98, the total number of people with stenosis, over the total number of people, 215. So you could build, if you now wanted to build your own expected values table, you could build that table now because you know that I'm going to guess that the prevalence is 40%, let's say. And you know that when you build your new table, 40% of 94 people will be in the yes, 40% of 121 will be in the no, if there was no association. Okay, so our null hypothesis is there's no association. We would get what we would expect to get in the expected values. Okay, well, okay, let's build the expected values. Okay, unlike what we did by hand, we can get SPSS to do it for us. Analyze, descriptive statistics, crosstabs, and this time I'm going to go into cells and I'm going to click off calculate the expected values for me too. I'm going to click OK. Okay, and here we are. There's the expected values. We count the real world and the observed values. We had 54 in the smoking and yes. We would have expected fewer, 42. In the people that didn't smoke, we would have expected, if there was no association, 55, but we in fact got 44. So it looks like there's a difference. The question now is the difference big enough for us to reject the null hypothesis? Okay, and how are we going to do that? We're going to calculate a chi-square value, and we're going to compare it to the chi-square value, critical chi-square value for 1 degree. Remember why it's 1 degree of freedom, right? 2 rows by 2 rows, 2 minus 1, 1, 2 minus 1, 1, 1 times 1, 1 degree of freedom. Rows minus 1, columns minus 1, multiply them together, and that's degrees of freedom. So we need a chi-square that's bigger than 3.84. We also need a p-value, a probability of being wrong, probability that we would get that value if there was an association. We want it to be less than 5%. Okay, so let's get it to calculate that for us. Analyze descriptive statistics, crosstabs again, except this time I'm going to go into statistics, and you guys might have noticed that there's a box up there for chi-square. In fact, it was glowing. It really wanted you to select it, right? I'm going to click continue. I'm going to click OK. And it's going to calculate the expected values, the observed values, and down here, Pearson's chi-square. That's, by the way, that's what this calculation is called. It's called Pearson's chi-square, is 9.84. Does that suggest to you that our p-value is going to be less than 5%? The answer is yes, because it's bigger than our critical value. In fact, our p-value, our significance, is 0.002. Okay. You might notice that SPSS calls this asymptotic significance two-sided. Based on what I showed you that the chi-square distribution looked like, you might say to yourself, why are you calling it two-sided? We're only working with one side of the chi-square distribution. I've heard a million explanations for why SPSS calls it two-sided. I never heard a good one, so don't worry about that. It works with that tail end of that chi-square distribution. Okay, so would we reject the null hypothesis? Help me out here. Yes, we would. We reject the null hypothesis because our chi-square value is bigger than our critical value of chi-square, and our p-value is less than 0.05. alpha that we would say. If I had told you that our alpha is going to be 1%, would you reject the null hypothesis? Yeah, I would still reject it because my p-value is 0.2%. It's still smaller than 1%, right? Okay, so now you'll notice that there's something else here called continuity correction. Okay, the deal here is that when you have a 2 by 2 table, when I calculated my observed values, I got even numbers, whole numbers. Why did I get whole numbers? Because there's no way to have a fractional person. When you're counting real people, it's always going to be a whole number, right? In other words, when you do your observed values, you're never going to get a fraction. But the real prevalence might be a fraction. In other words, in reality, in the expected values, it really might be 45.3 out of 100 rather than a whole number, right? So in order to make up for the fact that we're introducing a little bit of a bias because we're working with whole numbers in the observed values as opposed to the actual number in the expected values, in order to make up for that, the continuity correction says that when you take the observed minus the expected values, before you square it, you subtract 1/2. Half the difference, in other words, so it's kind of the midpoint between two numbers. Observed minus expected minus 1/2 squared over the expected values. And you do that for each box. I'm not going to ask you to do that, just so you know what the continuity correction is. Okay, you do it for 2 by 2 tables, typically only. Okay, and I think typically for small sample sizes. There's also some other rules that when I post the PowerPoint in the lecture, you'll see there's a few other rules, such as the minimum size of any one of these expected values has to be at least 5 or greater, and so on. Right, so you'll see some other rules, assumptions and rules that'll come up for this as well. Okay, so that's chi-square. That's what we're doing with chi-square. Okay, pretty simple concept, right? You could extend it now so that you're dealing with variables that have more than one value. For instance, if you wanted to know whether, for instance, smoking status. Smoking status could have been 2 packs or more, 1 pack, occasional, and none. So that's 4 rows, right? An outcome could have been 2 rows, aortic stenosis and no aortic stenosis. So you would have a 4 by 2 table. You would do exactly the same thing, except now you would have 8 boxes and 8 numbers that you'd have to calculate and add together to get the chi-square value. Of course, that would mean that you have 3 degrees of freedom. 4 minus 1 times 2 minus 1 is 3 times 1 is 3. So you would use for the critical value under degrees of freedom 3 on that table. So that might be 9 instead of 3. Yes.
Just a question, because I noticed that table wasn't uploaded. So are we only?
Oh, it's on Blackboard. I just got it. I think I just got it. I think it was right.
No, it wasn't. But
Oh,
it was
no.
there, yeah.
No, I think I opened it from my computer now that you mentioned chi-square stenosis. You're right. Okay, I'll make sure it's up there. Yeah, I'll make sure it's up there.
Are we generally going to do 2 by 2 tables?
Yeah, if you, as far as a test is concerned or something like that, maybe I might get adventurous on a homework or something like that. Probably not. You know where you might wind up with something that's more than a 2 by 2 table? After Thanksgiving, we're going to talk about a project. Project is going to be, I'm going to give you access to a database. It's a real database, the New York City Community Health Survey, right? Where they go out and they survey, I think, 20,000 people randomly in New York City. And they ask them about ethnicity, about their diet, about their weight and height, about, I think there's something like 200 or 300 variables that they interview them at. I don't know how they get people to sit there for that. I don't think they pay them, right? But they manage to interview all these people, right? And each year they put this data online. So in other words, if you wanted to examine whether different ethnic groups, right, ate more than a certain number of servings of fruit per week or not, right? That would be a categorical variable. Yes, they ate more than 5 servings per week. No, they didn't. And Hispanics, whites, blacks, American Indians, Pacific Islanders, so on and so forth. So that table would be a 2 by 4 table or something like that. So if you choose, and you'll have a lot of latitude with this, if you choose that you want to examine something like that, where it's two categorical variables, right? Then you can do that analysis, okay? And you can, so what you're going to be expected to do basically is you're expected to maybe give me a little bit of an introduction, what you're trying to show or prove, give me a little bit of a background, why are we interested in how much people eat fruit, give me a little statistical, descriptive statistics. What's the population you're looking at? Oh, the population I'm looking at is, if you're looking at ethnicity, you might tell me, oh, the population is 14% black, 42% white, 12% Asian, so on. So you give me a little bit of descriptive statistics, and then you do your test and tell me, I can say my null hypothesis is this. I can say with 95% certainty that there is a difference between the how much fruit, how many servings of fruit that different ethnic groups in New York eat, something like that. Now I'm going to show you one other thing that we can do with these tables. Okay, remember our table back here? Okay, our observed values. There's another calculation that we can do, and that is called, I'm going to put it on here first. Okay, I'm going to put up my observed values again. And it was 30 and 70, 100, and it was 10 and 90, 100 people, 40, okay, whatever, and 60, and so on. Okay, so what if I asked you, this is people that used the bath, and this is people that didn't use the bath, right? So what if I asked you, what's the risk of getting Legionnaire's disease if you use the bath? 30 out of 100, right? So the risk is equal to 30 out of 100 is equal to 0.30, 30%. That's the risk. What's the risk of getting Legionnaire's disease if you didn't use the bath? Well, 10 out of 100, the risk is equal to 10 out of 100 is 10%, right? Well, let me think. The risk if you use the bath is 30%. The risk if you don't use the bath is 10%. What if I divide that one by that one? 30% divided by 10% is equal to 3. That's called the relative risk. Sometimes they call it the risk ratio, right? The relative risk of using the bath versus not using it is 3. You're 3 times as likely to have gotten Legionnaire's disease if you were one of the people that had used the bath than if you hadn't used the bath. Okay. That's an interesting way of describing this, right? It's very descriptive. It gives you a handle on how big the risk is. So now the risk is 10% greater, or the risk is 20% greater, for a certain exposure. It's a nice way to quantify it. There's another thing you can do instead, and that's the odds. I'm not going to go, so we have very little time left. I'm going to get to the other building. I'm not going to go over it, but the odds are calculated a different way. When you go to the racetrack and a horse is going off at 2 to 1, what that means is it's not that he's twice as likely to lose as win. What it is, when horses at 2 to 1, it means that if they ran the race 3 times, he would win once, lose twice. Get it? It's a little bit different. If it would have been 2 to 1, normally you'd say, oh, it's 50-50 the horse will win. But really it's different, the odds. The odds are if they ran the race that many times, that's right. And they use that to calculate the betting return and stuff like that. It's a good way to calculate betting. That's why they do that. Well, in fact, in many studies, they do the same thing. The odds of getting ill if you use the bath, the odds are 30 out of 70. Right? Those are the odds of getting sick if you use the bath. The odds if you don't use the bath are 10 out of 90. So just quickly, 30 out of 70 is how much? 30 divided by 70 is equal to 0.43. Okay, and get it back again. And what did I say? 10 divided by 90 is equal to 0.11. I'm rounding these off just to save some time. 0.11, okay? And the odds ratio is the odds of getting the disease if you use the bath, odds if you don't not getting the disease if you don't use the bath, and it's 0.43 divided by 0.11, and that comes out to about 3.9 or something like that. They're in the same ballpark. They're not always the same. Now the odds ratio and the relative risk may not be exactly the same. Very often they're in the same ballpark. Many studies prefer to use the odds ratio for reasons I won't go into right now, but that's how you calculate the odds ratio. Let me ask you something. If there were no association between using the bath and getting disease, what would you think the relative risk or the odds ratio would be equal to? It'd be not zero. You got the right idea though, not zero. It'd be the same number, same risk, right? 1 be equal to 1. The odds of getting it would be whatever. The odds of not using the bath would be the same. The odds would be the same whether you use the bath or not. So when you put same numbers on top and the bottom, you're going to get the number 1. So what's our null hypothesis here? Null hypothesis is that the odds ratio is equal to 1, or the odds ratio is not equal to 1, right? And we want 95% certainty before we reject the null hypothesis. So another way of evaluating a table like this, besides chi-square, is to use odds ratio and relative risk. I'm going to go very quickly back to SPSS because I won't probably ask you to calculate the confidence interval for odds ratio to make sure that it's not one in between, right? That's how you would look. You calculate confidence interval for the odds ratio. It's a proportion confidence interval for it. And then you would see if the number 1 is inside that range, which means that you can't say it's different than 1, right? So let me go back to SPSS and just point out to you that one of the outcomes that we didn't pay attention to here was, let's see, I didn't tell it to do it. So I'm going to go, whoops, hey. I didn't tell it to do it, so I got to go back to analyze, descriptive statistics. Descriptive statistics, I don't need to hear from ESPN right now. Descriptive statistics, cross tabs. And I'm going to go into cells. And one of the things you can ask it to do, besides percentages by rows and so on and so forth, is you can, let me see, I'm in the wrong box. Statistics is I can ask it to calculate the risk. I'm going to click continue, say OK. And now when I get my result, when I look in this box, I see that the odds ratio for smoking status is 2.36. What is that saying? That's saying that the odds of getting Legionnaire's disease if you're a smoker are 2.63 times what it would be if you were not a smoker. That's the odds ratio calculated by SPSS. It also gives you a confidence interval here, doesn't it? And what does the confidence interval tell you? Well, we're 95% certain that the true odds are between 1.3 and 4.1. What's not between those two numbers for odds? 1 is not between those two numbers. So I know that if I'm 95% sure that the odds ratio is between these two numbers for the entire population, then I can say that it's different than 1. In other words, that I can reject the null hypothesis, that there's no difference in the odds. Okay? Is your head spinning? No, right? It's not that bad, right? Especially where we're gonna leave odds ratio, relative risk, and the confidence interval, and deciding on all that part. We'll leave that up to SPSS. The crosstabs and the chi-square is something that we could easily enough do with a calculator or with Excel or something like that. It's not really that hard that complicated a calculation.